Welcome to Significant Figures and Calculations. So, we've already talked about uncertainty in measurement, and we know that when we are making our measurements, we always want to strive for high accuracy and high precision. So in this way, our measurements have low uncertainty. But we need a way of communicating our uncertainty in our measurements, and we have two ways of doing this. One way is by explicitly stating the uncertainty. Let's say it's 25.00 milliliters plus or minus 0.02 milliliters. Right? We've explicitly stated our uncertainty is the plus or minus 0.02 milliliters. We don't really know that it's 25.00, maybe it's 25.01, 25.02, maybe it's 24.99, 24.98, but we're fairly certain that it's 25.00 plus or minus 0.02 milliliters. We're pretty sure that it's not outside that range. So that's one way, explicitly. The other way is implicitly, using significant figures. So if we say 25.00 and leave it there, 25.00 milliliters, the implication is that we're certain with our first digit, we're certain with our second digit, so we're certain with the 2, we're certain with the 5, we're certain with that first 0, but we're uncertain about that second 0. That's the digit that we're uncertain in. Now, usually we assume that we're uncertain by plus or minus 1 in that last digit. So in this case, this would be equivalent to the implication, at least, is 25.00 milliliters plus or minus 0.01 milliliters, not 0.02. So, significant figures are a way of tracking our uncertainty. Significant figures are digits in a measurement that carry meaning that contribute to its precision, that let us know how precise it is, how it gives us a measure of our uncertainty in our measurement. So we have a few different rules for significant figures. Non-zero digits, digits from 1 to 9, are always significant. So in this number, 0.001007500, the 1, the 7, and the 5 are non-zero digits. All the others are zeros. So those are always going to be significant. Now we have leading zeros. So we have the zeros out here. Those are different than these zeros and those zeros at the end. So leading zeros, zeros that precede all the non-zero digits, are not significant. They're just placeholder digits. They're just placeholder zeros. If I were to write this number without a decimal point, if it were a very large number, I would write it as 1007500, let's say. But if the decimal point was over here, I wouldn't need these 3 zeros in front. I wouldn't write them. They're just placeholders. They're just telling us where that 1 is, basically. And so those zeros, the leading zeros, are never significant. They're just placeholders. So they don't matter. Captive zeros are the zeros in between, so zeros between two non-zero digits, so between the 1 and the 7. It doesn't matter how many zeros you have in there. It doesn't have to be immediately in between, just as long as there are some significant digits on either side. So captive zeros are always significant. So these zeros always count. Right? So the 1 counts, the 0 counts, the next 0 counts, the 7 counts, and the 5 counts. Right? So we know that right now, those 5 digits count for sure. And then we have the trailing zeros, those 2 zeros at the end. Right? So trailing zeros, zeros to the right of all the non-zero digits. Right? So these 2 zeros are not trailing zeros because they're to the left of some of the other non-zero digits. But those zeros are trailing. So the trailing zeros are significant only if our number contains a decimal point. So this number does contain a decimal point, so these zeros are significant. Those count as sig figs. But in this case, there is no decimal point. We haven't written one. So if there were a decimal point, it would be here. But because we haven't written a decimal point, these 2 zeros don't count. They are not significant. So what we're saying there is we're uncertain in the 5 place. However, if we write a decimal point, 1007500 decimal, now we have a decimal point. So now those zeros count. Right? So if you see a number that ends in 0, like this, in the ones place, with a decimal point, that 0 counts. And any zeros to the left. So this number is not the same as if I don't have that decimal point there. So you need to be very careful. So now the next rule is that exact numbers are considered to have an infinite number of significant digits. Now remember, we've already talked about the difference in a previous video about counting and measuring. Measurements are never exact. They can't be. Because we're always comparing some physical object against a scale. We can't be exact with that because it's our interpretation. But counted numbers are exact. If I'm counting the number of people in a room, assuming I haven't made any mistakes, I know exactly how many people are in the room. If I count 7 people in the room, it's exactly 7. It's not 6.9 or 7.1. There's no uncertainty in that number. Again, we're assuming that I've counted correctly. So exact numbers are numbers that are not obtained by measurement. Counting is not measuring. So obtained by counting or from definitions. So if we define 1 inch as 2.54 centimeters, which is how it's defined, that 1 and this 2.54, because it's a definition, those numbers are exact. So what we mean here, if it's an exact number, we're sort of saying, well, it has an infinite number of significant digits, because we're saying there is no uncertainty. We know that it's exactly 1 inch. It's not 1.00000001 inch is equal to 2.54 centimeters. It's exactly 1. 1.0, where 0 repeats forever. There's no uncertainty in that value. So all digits in a number expressed in scientific notation are also significant. So if we wanted to write this number, right? Remember, we know that the 1, the next 2 zeros, the 7, the 5, and the following 2 zeros count. These last 2 zeros count, remember, because we have a decimal point. We need to write all of those digits that count. So all of the red digits there need to be written over here. So if we write that in scientific notation, we have 1.007500 times 10 to the minus 3. We have to include those 2 zeros here because they were significant there. Which also means that if we have some zeros in the scientific notation, they're significant. Because again, we never write in scientific notation, we never write something like 0.1 times 10 to the minus 2. We don't write it that way. We would write it 1 times 10 to the minus 3. So any digit that's not part of the 10 to the minus whatever, any digit that's over here, those digits always are significant. Those always count as sig figs. So, again, we're uncertain about the value of the last significant digit. We still call it significant because it's a guess. It's an educated guess, but it's still a guess. So we're uncertain in that value to some degree. And generally, we assume that the uncertainty in that last significant digit is 1. So 25 milliliters means 25 milliliters plus or minus 1 milliliter. So maybe it's 24 milliliters, or maybe it's 26, or maybe it's 24.8 milliliters. We don't know. All we know is that it's somewhere between 24 and 26 milliliters. But if we write 25.00, now that means 25.00 plus or minus 0.01 milliliters. So now we know that it's not 24 milliliters. We know that it's not 26 milliliters. We know it's not 24.8 milliliters. We know that it's somewhere between 24.99 milliliters and 25.01 milliliters. Right? So here, we're much more certain about our volume measurement than we were up there. So when you're in the lab, you need to be very careful about how certain you are. Look at your piece of glassware, and they generally are labeled with some uncertainty value. It probably won't be 0.01 milliliters, but maybe it is. Depends which sort of glassware you're using. So you need to write, if you measure it as 25 milliliters, you need to write down however many decimal places with however many zeros, if the zeros really should be there. Now, don't just go writing zeros in if you're not sure. You need to know exactly how precise your measurement should be. How many significant digits should you write down? If you're going and measuring on an analytical balance, if it's got a digital readout, you should be writing down all of the digits that are there. You should know exactly how much, what the mass of your object was. So, if we want to use significant figures in calculations for multiplication and division, the result should be written with a number of sig figs equal to the smallest number of sig figs of all the numbers involved in the calculation. So here I have a relatively simple example where we have two numbers, one number being divided by a second number. So we have 5.0450 grams divided by 6.7 milliliters. So how many significant digits does each one of these numbers have? Pause the video if you need to and figure it out. So the top number has 5 sig figs. Right? This is a captive 0, so that one counts. This is a trailing 0 with a decimal point, so that 0 counts. So we have 5 sig figs here, 5 sig figs, and we have 2 non-zero digits here, so 2 sig figs there. So let's see. Our result should be written with the number of sig figs equal to the smallest number of sig figs. Well, 2 is smaller than 5, so our answer needs to have, our result needs to have 2 sig figs over here, so that's why I've written 0.87. Remember that 0 is a leading 0. Leading zeros don't count. So the 8 counts and the 7 counts. So this is 2 sig figs. That's what we should write. We don't want to write any digits past that. Now be careful, because you need to round the next digit, right? So if the next digit, if it's 0.874, you want to round down. If it's 0.875, you want to round up. So that'll become 0.88 grams per milliliter. But you don't want to round all of the digits, right? Just this place, just the last significant digit. So that was for multiplication and division. For addition and subtraction, the result should be written with a number of decimal places equal to the smallest number of decimal places in the numbers involved in the calculation. So here I'm saying decimal places, not sig figs. So we need to match up the decimal places. So if we have a case like this, 5.0450 grams plus 6.7 grams, if we move this over and line up our numbers, we have 6.7 grams. So the second number, 6.7, has fewer sig figs, but it also has fewer decimal places. So here we have our last decimal place is the tenths place. Here our last decimal place is the, let's see, tenths, hundredths, thousandths, 10,000ths place. So we know the top number to significantly greater precision, significantly less uncertainty, than we know the bottom number. But that means that we don't know what these other digits are here, so our answer doesn't make sense to say 11.7450, because we don't know what the rest of those digits really ought to be. We don't know what these digits are, so we don't know what the sum is. So, we're writing 11.7. But note, our answer now, 11.7, that has 3 sig figs, whereas our 6.7 here only had 2 sig figs. Right? So we may end up changing the number of sig figs. On the other hand, we may have fewer sig figs if we're subtracting these numbers. Well, in that case, if we did 1.7, so we'd still have 2 sig figs. But if this was 5.7, well, then our answer would just be 0.7 grams. So, note that if you're performing multiple calculations, it's best to keep extra digits around and round only at the end of your series of calculations. Because if you do, say, if you have a whole string of multiplication or division, if you're rounding after every calculation, you could end up introducing some significant rounding errors. So the best thing to do is, if you have a bunch of calculations that you're going to do and you only care about that last result, only round for that last result. So if you have a whole bunch of these, keep more digits than what you really ought to have. If you want to, label your significant digit with an underline to keep track in your head of, or rather on paper, of which place you ought to be rounding to. But keep digits past that until you get to the end and then round it, and now you're only rounding once, and so you're not very likely to introduce any rounding errors. So that was significant figures and calculations.